Chapter 5, Laws of Motion. As you're seeing, the clouds are moving. Similar way, we do have things which used to move around us in our everyday life, in each and every moment, right? How these objects are going to be getting into motion, that's what this thing is going to be the one what we'll be learning with this. You could able to see a car moving, a flight which is going to fly, and a butterfly can also fly. All this could able to move from one place to another. That means that they are having the change in position. The car starts at a different position and it goes and ends up at a different position, right? So what is this different change in positions the objects are going to have can be defined with a single term which is called as motion. So basically the motion is defined as the change in position of the object with respect to time. Aristotle's fallacy tells us how the object moves. The movement of the object is associated with force, but the force is going to be decided by how heavier the mass is. That is what is the Aristotle's fallacy is telling us about. For years, Aristotle thought about the moving object was ruling. Aristotle preached that the heavier objects move faster than the lighter objects, by stating that the speed at which something falls actually depends on its weight. He would explain anyone who listens by stating the example that is an object weighs 10 times heavier than the another will have to fall 10 times faster. No one disagreed with Aristotle. Most people were comfortable with this concept as the heavier objects falls faster because that is what they observed. For more than 2000 years, Aristotle's rules for falling objects remain unchanged unless a new scientist attempts to prove him wrong. We could able to see the fact why the Aristotle's fallacy is not true. It's not applicable to all kind of situations as well as the objects. Out of that, the baseball, which is going to the falling one, and the lack of direction with the contact, and when the object is going to have the force and velocity in a different direction. But all this are being compensated by Newton's laws of motion. But why Aristotle's fallacy was not working? Let us look into an example with the help of the following clip. We are having two balls which is having a different masses. One is of 5 kg, the other one has been filled with air. So we are going to give this to different peoples over here and we are going to try it out when we are going to drop them, whether they are going to move with the same amount of time or the time varies. That is, the heavier ball moves faster according to Aristotle, right? Let us look into that now. So we are just giving the ball to the different persons over there. Each and every one of them are going to have a trial with this. The ball is going to have the same radius as well as the size of the ball are going to be the same one. There is no change in that. When the question has been asked to everybody, the answer is the more heavier ball will be falling down faster. Because it's due to gravity, that means that the more heavier the ball is, the higher gravity it's going to have. So the gravity is the answer given by everybody. As the higher masses, it will be pulled towards the downward with higher force, right? So the trial is going to start over now. Everybody is going to hold both the balls at the same height and they are going to drop it. Observe it properly. whether they are coming down at the same time. Got it? Go? Yes. So as you're seeing it over there, both the balls came down at the same time. There is not much time difference in that. What is the reason behind it? Because the ball movement is going to depend upon the amount of force acting on it, obviously, but it depends upon the inertia of the object. What do you mean by this term inertia? The tendency of the object to be in the same state. This inertia is going to depend upon the mass of the object, but not purely. Okay, so when it's going to come for the concept of inertia, the different objects will be moving with different speed. That's true, but you could able to see the two balls, what we are going to have it over here. The heavier it is, then it will be having higher gravity. That is true. But when we are going to drop both of them from the same height, the gravity varies, but the amount of acceleration acting on that will be same. That is, the ratio of the force to mass will always remain same on the object what we are going to have. Let us have a look at it. Both the balls are going to be dropped down. The amount of force acting on them varies, gravitational force. But when they are going to fall, it's inertia which makes them to bring it down, right? So the size of them, there is mass and the velocity of them will remain same. So both of them will reach the down at the same time, right? Now by concluding all this, we can say the Newton's first law of motion, where the Newton's first law of motion is going to tell us the same thing, that the tendency of the object to be at rest or to be in movement will be remaining same until otherwise we are going to have an external force acting on it. Very simple example, Tom is sleeping over there, right? If Tom wants to wake up, then Jerry has to do something about it. Or let us take ourselves, when we are sleeping in our home in the morning, either our parents have to come and wake us up, or otherwise we have to get the sound of an alarm. We have to get the sound of an alarm. Let us take the example that the Newton's first law of motion. The Newton's first law of motion is also going to tell us the same thing, that the movement of the object is going to depend upon the external force, but it's going to be said in terms of the inertia. Unless otherwise an external force acts on the object will try to remain in the same state of rest or movement, or it will follow the same direction. If you are going to look at this over here, Tom is sleeping over here. Tom will not wake up until otherwise Jerry does something over here. In our case, our parents or our siblings will be doing the Jerry work, right? If you are sleeping, most of the time we will not get up on our own. We need an alarm or we need someone else to come and wake us up. So that alarm sound or the voice of someone who is making us to wake up is the external force. Without that external force, we will be at the rest only. We will not get into motion. You could able to see it over here. We are at rest. The external force appears. We are back, right? Yes. And when it's going to come for the overall definition for that, the ball is at rest over here. So an object is at rest, will remain at rest until it receives an unbalanced force. So you're kicking it, you're supplying an unbalanced force on it, right? Now you could be able to see that the ball is moving and you got a goal, right? So that unbalanced force making the rest object to get into motion. The reverse is also applicable. A moving object can also come to rest, like applying a brake to a car what we were driving, right? Yeah. So this is how the Newton's first law works. When it's going to come for the Newton's second law, it's like we all would love to do it, right? We like to go for shopping, and the trolley is the most most favorite one which we wanted to push over the rest. But when you are going to get enter into the shopping mall, then the trolley will be empty. That means it will be very easy for you to push. Even with your finger you'll be able to push it. Am I correct? But now shopping got over, we fill everything whatever we wanted to fill inside the trolley, right? Now if you wanted to push this trolley, one finger or just the finger won't be enough. Am I correct? The force need to be increased. That means that initially it was at empty, so that you need less amount of force, a finger push. When it's having higher mass, then you need more force. That means that more mass, more force. Am I correct? And you could be able to see one more example for it over here. The actual elephant is there as well as the toy elephant is there. I'm asking you to push the actual elephant which is standing in front of your home now. Is it possible for you to do it? Yeah? Fine, it's not possible for us to do. But when it's going to be a toy elephant, even you can kick it with the help of a single finger, the force that is more than enough. Am I correct? So here also the same thing plays the major role. More mass, more force required. Less mass, less force. Both of them are relevant, but the original one is going to have 1000 kilogram of weight. But the toy one will be having the mass of that as only few grams, right? So less mass, less force required. That's what the second law is telling us, that the amount of force what you have, that's going to be directly proportional to the mass associated with that. Similar way, it will be directly proportional to the acceleration associated with the object as well. For example, you could be able to see the force of girl accelerate the box. The force is going to be the same thing which is going to be given by the girl. Now the mass got increased. See, the acceleration, that is the movement of the object, is going to be reduced. Force remains same, but as the mass increases, acceleration of the object reduces. When it's going to be 3 times, then you were able to see furthermore the acceleration got decreased, but the force remains same, right? When it's going to come for that explanation, the acceleration of an object is going to be directly proportional to the mass of it, and it will be inversely proportional to the mass of the object. So when it's going to come for the definition, the force acting on the object will be directly proportional to the acceleration, and the force is going to be directly proportional to the mass, but acceleration is going to be inversely proportional to the mass, as well as the acceleration is directly proportional to the net force acting on the object, which can also be said in terms of the statement that the rate of change of momentum of a body will be equal to the amount of force supplied on the object. Now we are coming for the last one, which is going to be the Newton's third law of motion. You could be able to see the boy over there. He was just trying to do a water racket, right? He was pumping the water, half-filled water bottle, with the help of the air pumper, right? As you're seeing it over here, at one point of time, the amount of air what he pressed inside it is creating a high amount of pressure. So with that pressure, the bottle is moving forward, and it's giving a reaction force with the help of what? The boy as well as that pump is moving towards the backward. So the Newton's law says is that wherever there is an action, there will be an equal and opposite reaction. You were able to see these are the classical examples. Whenever you are going to move out of a boat, the boat, you will be moving towards the forward, which is the action. As a result of it, there will be an action force on the boat, so that the boat will be moving backward. Yeah, and you could able to see it over here. When you're going to sit on a chair, if there is no force is being given on yourself, then you will be pulled towards the downward with the help of the gravity, right? So there is a force which balances in the upward direction, which is called as the normal force, because of which we are not falling down. And another classical example for the Newton's third law of motion, recoiling of a gun. The gun, that is the bullet, moves in the forward, but the gun is going to move in the backward as a result of the reaction force what we are going to have. So ultimately the statement is, whenever you have a movement of an object, always it is going to have two forces associated with that. One is the action force, the other one is the reaction force. Here, when the balloon is going to be opened up, you will be having the air released out, which is going to be the exhaust action, which is in the forward direction, but as a result of this forward exhaust of air, the balloon will be moving in the backward direction, right? So Newton's third law says us that the action, if you're going to have, it will be having an equal reaction force as well, but it will be in the opposite direction. Hope all you understood the concepts what we have.